We will begin the second part of lesson 4.2 by discussing how to measure radiation. Is it possible for us to measure the radiations like alpha, beta and gamma? What is the method and what is the principle used in measuring the radiation? Now, when these radiations go through air, you see, air is made up of atoms of different substances like oxygen, nitrogen and so on. When these radiations go through air, these radiations can knock off electrons from the atoms and ionize the atoms of air. Now, when ions are produced in air, air becomes conducting. You can pass electricity through it. And we're going to use that property to measure these radiations. Now, radiation can be measured using the effect they produced. Now, what effect are we going to use to measure radiation? The effect of producing ions in air. Most radiations knock off electrons from atoms in a material producing ions. I hope that is understandable, because in an atom the nucleus is surrounded by electrons, and if radiations pass through, some of them can hit the electrons and knock them off the atom. That means the remaining atom will be a positively charged atom, or it will be called an ion. And when there are many such ions in that air becomes electrically conducting. An electric current will pass through that air. Normally, air does not allow electric current to pass through it. An ionization counter, a counter used for measuring radiation, is therefore called an ionization counter. Why? Because these radiations will produce ionization, and the ionization is then used to count these radiations. So we call it the ionization counter. Radiations also produce flashes or sparks when they fall on phosphorus materials or fluorescent materials. So if you allow radiations to fall on a material coated with a phosphorus material, the moment the radiation falls on it, it produces a flash. That way you can actually count it. So there are many ways of measuring radiations. Most commonly used radiation measuring device is a counter known as the Geiger counter. The Geiger counter, because it is the scientist Geiger who developed it. Now, this is actually a Geiger counter. I will show you one in a minute. Well, let me show you how the principle of action of a Geiger counter. How does it work? Now, this is the schematic diagram of a Geiger counter. I want you to pay attention and listen to the working of this. Now, radiation is received in a metal tube. Now, this is the metal tube. Let me show you the one I have here. Now, this is a Geiger counter, and this is the metal tube which I have drawn here. And inside the metal tube there is a metal wire. And now you apply a very high voltage between the wire and the outer part of the cylinder. The outer part is made negative and the wire is made positive. Here you can see the electricity going into that wire. The metal part I'm holding is negative and inside it is positive. That means as long as this air remains normal air, it will not allow an electric current to flow through it. You see, this is negative and this is positive. If this air allows electric current to flow through it, a current will flow in that circuit. Now, as long as this air is normal air, there will be no current flowing there. But when a radiation passes through it, what will the radiation do? The radiation will produce a lot of ions along its path. When a radiation produces ions, the air will become conducting. It will allow electric current to flow through. That means electric current will now flow from this central wire to the tube, completing the electric circuit. And when it does, it will either produce a sound or it will count the radiations. Now, I have this counter here which is connected to, now this is connected to a counter here. You can see this is the counter. Can you read what is in there? Well, I think I'm going to keep it to the shade. Yes, you can read it as 519. Now, it's actually counting the radiations in this room now. You see, I turned it on about half an hour ago and it has already counted 524. Each time a radiation comes in, you can see a flash. Can you see? Yes? What's the flash? Each time a radiation comes in, it flashes and it counts for you. There you are. Alright, watch for the flash. Each time a radiation comes in, you will see a flash there. Alright, let's see if the next one is going to come in. There. And the count will be registered. Well, so each time a radiation comes inside the tube, each time a radiation comes inside the tube, along the path of the radiation there will be ions produced, which means the air inside becomes electrically conducting. A pulse of electricity will go through and that pulse of electricity will be registered as a count. Now I have a smaller counter here which I'm going to turn it on. Let me see. Now if you notice here, I'm going to keep it in front of the camera and see whether you can actually see it. There you are. Every time a radiation comes in, it will produce a sound for you. Now, listen to this sound when the radiation comes in. So it counts the radiation and also gives out the sound for you. Well, you can also see the flash there. Each time a radiation comes in, there is a flash. It counts. Also, you hear the sound. So this is a very good radiation counting device. Now, you see, the sound you hear now is due to the background radiation. There's always some radiations around. And when that radiation passes through this tube, it counts it for you. Now, look at this material. Can you recognize what this is? This is part of a porcelain plate. When I hold it next to this, the count rate goes up. Can you hear it? Well, what does that mean? It means when you eat in this plate, you are actually eating in a very highly radioactive material. So most of the material that you have around you is radioactive. I have another material here which is actually, this is the mantle of a lamp. Now hear that. It's going crazy counting the radiations. You see that? Within a short period of time, it has counted now over 500 radiations. So there are so many things around you that are radioactive. So you are actually surrounded by radiation, and the radiation present in any space is called background radiation. We will actually do a lab to measure background radiation. Well, an insulated wire inside the tube is connected to the positive of the battery, and the metal cylinder is connected to the negative terminal. Alright, no current flows between the metal wire and the cylinder because the gas inside is an insulator. Normally, it is an insulator. When radiation passes through the window, it ionizes some of the gas atoms inside, producing free electrons, and these free electrons will make the gas electrically conducting, and a pulse of current will flow, and that is then amplified so that you hear that sound and it registers a count. So that is a very good way of measuring radiation. When connected to a counter, these current pulses produce click sounds or directly registers the number of counts, or it does both in the case of the small counter I showed you. Now, what are some radiation units? What are the units in which we are going to measure radiation? The number of decays per second or activity per second from a sample of radioactive nuclei is measured in a unit called becquerel. Now that name is familiar to you, is that right? Becquerel is the person who discovered radioactivity, and it is abbreviated BQ. So what is a becquerel? The number of decays per second is called becquerel. Now 1 decay per second equals 1 becquerel. Now, if 1 decay per second is 1 becquerel, how many becquerels did we have here? We had about 500 in about 30 seconds. So you can see that radiation produced by these simple materials is a large amount of radiation. Now, an older unit is called Curie. It's after Marie Curie, named after Pierre and Marie Curie. 1 Curie is approximately the activity of 1 gram of radium, and that is equal to 3.7 times 10 to the power of 10 becquerel. What that means is, if I have 1 gram of radium here, there will be 3.7 times 10 to the power of 10 decays or disintegrations per second. Can you imagine? That's a very big number. Now, almost 37 billion disintegrations per second. So, if we have that in front of this counter, it will make 37 billion sounds per second. Well, we will not be able to hear individual sounds. It will be a very uniform sound. The amount of radiation received by a human is expressed in terms of radiological dose. It's called the biological dose. In other words, if you want to measure the radiations that we are getting exposed to, we use a different unit for that. Now, radiation dose is measured in a unit called rem. The natural radiation that people receive in a day is about 1 millirem. As I told you, we are always exposed to radiations from the background. And normally, the normal radiations that we are exposed to is about 1 millirem. The SI unit for radiation is called the sievert, the SI unit for radiation. Now, I would like you to remember some of these units. Okay, let's now talk about a lab, the last lab we will be doing in this course. Now remember, there are altogether 12 labs and you are supposed to send me a minimum of 10. I will grade 10 of your labs. Alright? Now, the radioactivity is a random phenomenon. So there's no rule guiding it. Now, if you have a nucleus of an atom that is unstable here, there is no guarantee that it will be undergoing disintegration now or anytime soon. There is no way we can decide. It is a random process. So radioactivity is a random phenomenon. The distribution of radiation rate is expected to follow a normal distribution pattern. In other words, if we use this instrument to measure the number of radiations for a period of 1 minute, and if we measure it for about half an hour, now, do you think each minute you get the same number of radiations? No, it will be completely different. Each minute you get a different number of radiations. Now, how will they be distributed? You see, one characteristic of a random phenomenon will be they follow a normal distribution. We call it a bell-shaped distribution. Now, if you have heard anything about statistics, you will understand the meaning of a bell-shaped distribution. Well, we're going to look at the distribution of this. I measured the background radiation of this room for 42 minutes. I took the counts for each minute. I used actually this equipment. I turned it on and I can set it for each minute count. It will count for a minute and will give me that number. And then I do it for the next minute. I did it for 42 minutes and I got these numbers. Now, the first minute I had 25 counts. It means there were 25 radiations detected in this room in the first minute. The second minute there were 17. Third minute there were 12. Then 22, 21 and so on. And I did the experiment for 42 minutes. I spent most of my morning doing this experiment because this is the one I'm going to use it to show you. I did another sample for you to work with. Alright, you know what I did? I divided these values into 7 classes. Now what does that mean? Now if you look at these numbers, there are numbers greater than 20, numbers between 15 and 20 and so on. So what I did is I counted how many numbers are from 5 to 7. If you look in here, watch here. I have, well, there is a 7. There is anything else in that class? Yeah, there's a 5. So in this group, that is how many 5 to 7 are there? There are just 2. There is a 7 here and there is a 5 there. So from 5 to 7 there are 2 values. Now how many are from 8 to 10? Now what I did is I wrote each numbers. You see, you can go and do like this. Let me show you how to do that. Okay. I wrote these like this. Alright. Greater than 5, greater than 10, greater than 15, greater than 20. I sort of classified like that, and when I take each number, 25, I write 25 here, 17 I write here, 22 I write here, then 21 I write here, 9 I write in the top one, 12 come here, 16 is here. So you look at the way I'm dividing these. I said how many are above 5 and below 10. All those I will write here. And now, using that, I counted the numbers from 8 to 10. I got 6 of them. 11 to 13, I got 10 of them. 14 to 16, I got 11 of them. 17 to 19, there were 7. 20 to 22, there were 4. And 23 to 25, there were 2. You see, there is a 25 there, and there is a 23. There you are. So this 23 and 25, there are 2 of those between 23 and 25. Now, these numbers are called the frequencies, and these are called the classes. You see, my class 1 is 5 to 7. There are 2 values in that category. 8 to 10, there are 6. So 6 is called the frequency of that class. Now, this is the way these radiation counts are distributed. And now, I don't know how many of you know how to draw a histogram. I can now use these numbers to draw a histogram to see how these numbers are distributed. I'm going to take you to the next slide and show you that. Alright, now I have brought this over. These are the classes, these are the frequencies, and I'm going to show you how I drew the histogram. Now, a histogram is a graph. This is the x-axis, and this is the y-axis, and I'm going to draw the frequencies, that is, these numbers on the y-axis. The maximum I have is 11, so I'm going to go in steps of 2. Look at this, 2, 4, 6, 8, 10, 12. I need only go up to 12 because 11 is my maximum. And I go to the first class. In the first class, I have 2 values. Look at that. I draw a rectangle that has a height of 2. This represents the frequency of the first class. Now, the frequency of the second class is 6. I draw another rectangle that represents 6. The frequency of the third class is 10. The frequency of the fourth class is 11. The frequency of the next class is 7. And the frequency of this class is 4. And the last class is 2. So once again, and look at the distribution there. Well, let me go back there. Now, this distribution is called a bell-shaped distribution. It is a normal distribution. Any random process has a normal distribution. So, the radiation that you have around here, the background radiation, is a random process, and the distribution of that is normal like this. Okay, now this is what I did. Now I want you to do a similar exercise and send it to me. And in order to do that, I did a second trial. I did a second trial and measured the background radiations for 42 minutes and obtained these values. Alright, now you need to work with it. Divide these into 7 classes as shown below and count the frequency for each class. So I've given you the classes. How many values are here between 5 to 7? How many values are there between 8 to 10? How many values are there between 11 to 13? Alright, when I say between 11 to 13, both those numbers are included. How many are there from 14, 15, 16? How many are there 17, 18, 19, and so on? So fill in the frequencies and draw a histogram of these frequencies. Alright? And complete the worksheet. I have also asked you some questions, a simple question based on what we did. Alright, and complete this and email that to me. Make sure that you have now completed all the labs. Okay, we will now talk about nuclear energy. Nuclear energy. Now, this is the time when everybody is actually talking about nuclear energy. The world is actually facing an energy crisis, aren't we? Yes, we depend for most of our energy needs on the fossil fuels, coal and oil mostly. And you know, oil is bound to run out one of these days. And look at the price of oil that is climbing. It is nearing $100 per barrel. And maybe before you hear my lecture, it must have crossed $100 a barrel. You can see it's becoming a more and more difficult and rare resource. We need to explore the possibility of other energy resources. And one possibility is to make use of the energy that is locked up in the nucleus of atoms. Alright, now the energy that holds the nuclear particles together is called binding energy. I had introduced that earlier. You see, to hold all the particles together, you need a tremendous amount of energy. And that energy that is used to hold the particles together is called binding energy. Now, if by any means, if you can break the nucleus of an atom into pieces, the energy that is holding them together is no longer required, and that energy will be released. You can actually make use of that energy. We can use it to produce electricity. You see, that will be a great help for us. Now, when nuclear particles escape the nucleus, part of the energy holding these nucleons together is released. And this is the origin of gamma radiations. If a massive nucleus splits into 2 pieces, the binding energy holding the pieces together will be released. And that is the origin of nuclear energy. The total mass of the pieces is less than the mass of the nucleus. You see, if this is one nucleus, and if you measure the mass of this now, and when it splits into 2 pieces, it is found that the sum of the masses of the 2 pieces is less than the mass of the original nucleus. That means, what happened to that small difference in the mass? That mass became energy. You see, Einstein showed that mass can be made into energy. So this lost mass, this small mass difference, is called the mass defect. And according to Einstein's equation, E equal to mc squared, I'm sure some of you must have heard about this equation. It means a mass can be made into energy. You see, if I can get all this mass converted to energy, there will be enough energy to produce electricity to run the whole of Florida for a year. That much of energy is locked up in this matter. So when a small mass gets converted to energy, it follows this relation E equal to mc squared, and this mass defect, that is the mass difference between the pieces and the original material, is converted to energy. The binding energy of the nucleus of any isotope can be calculated from the mass defect of the nucleus. We will soon talk about binding energy per nucleon. Now, the binding energy per nucleon is an important indicator of the stability of the nucleus. You see, how stable the nucleus is indicated by the binding energy per nucleon. Now, what is the meaning binding energy per nucleon? Let me see if I could show an example. Suppose you have a nucleus here. This is the nucleus that contains 100 nucleons. Now, do you understand, do you remember what nucleons are? Nucleons are the total number of protons and neutrons. Suppose this nucleus contains 100 nucleons, and if the total binding energy holding all those nucleons together, let's say, is 1000 joules. Energy is measured in joules. Is that right? So, suppose the total binding energy of this nucleus is 1000 joules. And this binding energy of 1000 joules is used to hold these 100 nuclear particles together. Now, what is the binding energy per nucleon? If you divide the total energy by the total number of particles, you get binding energy per nucleon. Now, this is like this. If I have 1000 M&Ms, and if I distribute that to 100 students, what is the number of M&Ms per student? It will be 1000 divided by 100, 10. Each student will get 10 M&Ms. Similarly, a total binding energy of 1000 joules is for 100 nucleons. So what is the binding energy per nucleon? It is 1000 joules divided by 100, which is 10 joules per nucleon. Now, this measure is an important indication of the stability of the nucleus. Okay. Now, look at this diagram. It gives you a measure of the binding energy per nucleon. Now, here I have the number, the mass number. Remember, the mass number is the number of nucleons. Mass number, this is the number of protons plus neutrons in the nucleus. Now, that means the binding energy per nucleon for small elements like helium, it is very small, but as the nucleus gets bigger and bigger, the binding energy per nucleon increases. Now, when you come here, this is the maximum amount of binding energy per nucleon. Now, which element is there? This is iron, which has a mass number of 56. You see, this is mass number 40, this is 60. So, mass number 56 is iron. Its atomic number is 26. And its binding energy is about 9. The unit used there is a unit called million electron volt. You don't need to worry about that. So, iron has the maximum binding energy per nucleon. That means iron is the most stable element. as the binding energy per nucleon decreases, you can see it decreases on the left and also decreases on the right. That means as you go to the right, as the nucleus becomes bigger and bigger, binding energy per nucleon becomes less. And those nuclei are very unstable. So that means nuclei that is here, over here, look at uranium. The nuclei of uranium are very unstable, and sometimes they can split into pieces, so that each piece will have a binding energy somewhere in this region. Alright. The greatest binding energy per nucleon occurs near mass number 56, then decreases for both massive elements and light elements. So binding energy per nucleon decreases to the left. As the elements become lighter and lighter, the binding energy per nucleon decreases. So tell me, if these lighter elements want to become more stable, what should they do? They must fuse to become bigger element so that their mass will become close to this to become more stable. So lighter elements, when they fuse together, they become more stable. And heavier elements tend to break apart in order to become stable. Okay. Now, more massive nuclei can gain stability by splitting into smaller nuclei, increasing their binding energy per nucleon. So a nucleus of uranium that is here, which has a very low binding energy per nucleon, if it splits into two pieces, each piece will have a binding energy per nucleon greater than the parent nucleus. So uranium is a good candidate for splitting into pieces. Conversely, less massive nuclei, that is lighter nuclei to the left, will gain stability by combining together. And the process of lighter elements combining together is called nuclear fusion, combining together. So one way to produce nuclear energy is use the process of nuclear fusion. Another way to produce nuclear energy is to make massive nuclei to split into pieces. And that process is called nuclear fission. Now, the slopes of the red line shows these processes, indicating that more energy is released when smaller nuclei fuse together. In fact, the nuclear fusion is a much more efficient way to produce energy. Look at this. The slope of this line is much greater than the slope of this line. So when lighter elements fuse together, they release a tremendous amount of energy, much more than when heavier elements split. The amount of energy they release will not be as much as in fusion. Well, let's now talk about nuclear fission. What did I say the process of fission is? Fission is the process of a big nucleus splitting into two pieces, so that each piece will be more stable than the parent nucleus, so that each piece will have a binding energy per nucleon close to the stable value. The process of splitting a massive nucleus into more stable, less massive nucleus with the release of energy is called nuclear fission. Now here I have illustrated the process of fission of an isotope of uranium. You see, uranium-235. How many of you remember the atomic number of uranium? What is the atomic number of uranium? It is not written down here. Uranium is of atomic number 92. And uranium has two main isotopes. One isotope is uranium-238. We talked about it in the last class. Another isotope is uranium-235. Now, this isotope, uranium-235, is very rare. Of all the uranium that is naturally available, only about 0.5% is uranium-235, a very small quantity. Now, this is a very important material because this will undergo fission almost spontaneously. Now here, this is the atom of a uranium-235. This is the nucleus of a uranium-235 atom. Now, if it gets a neutron, the moment it absorbs a neutron, it undergoes fission. It breaks into two pieces. One piece is rubidium and the other piece is cesium. You see? When this breaks into two pieces, each piece is stable, and along with breaking, it releases tremendous amount of energy, and also it releases free neutrons. You see? The important thing is, it is a neutron that causes the fission, and the fission itself will release free neutrons on an average. You can see here, this is a free neutron, this is a free neutron, and this is a free neutron. Sometimes 3 neutrons, sometimes 2 neutrons, but some number of free neutrons will be made available for each fission. Now watch this animation. A uranium-235 absorbs a neutron, it splits into rubidium and cesium and a great amount of energy. It also releases 3 neutrons. Can you see that happen? A neutron is absorbed by uranium-235. It splits into rubidium and cesium. It releases energy and also 3 free neutrons. That is the process of fission of uranium-235. Fission can occur when the nucleus of a heavy atom captures a neutron. In addition to energy, free neutrons are released during fission. Now, this is another schematic diagram for that. A neutron comes in and is absorbed by the uranium-235 atom. It splits into 2 pieces, releasing a lot of energy, and also it releases on average about 3 neutrons. Alright, so this is the process of fission. A uranium-235 nucleus absorbing a stray neutron will result it to undergo fission. Now what are the fission products? The fission products are, well, you have cesium and krypton. It doesn't matter the names. There are 2 new elements and free neutrons and a tremendous amount of energy. Materials that undergo fission are called fissionable materials. Fissionable materials. Not every material, not every heavy element will undergo fission. One good fissionable material is the isotope of uranium called uranium-235. So uranium-235, uranium-233 and plutonium-239. Now these are some good examples of fissionable materials. Most commonly used fissionable materials are uranium-235 and plutonium-239. The fission of uranium-235 in reactors is triggered by the absorption of a slow neutron, often termed a slow neutron or called a thermal neutron. So in a nuclear reactor, the fuel used in a nuclear reactor contains uranium-235, the fissionable material, and it will undergo fission once it captures a thermal neutron or a slow neutron. In fact, if I keep a uranium-235 lump of material here, it will absorb a neutron from the surrounding and will undergo fission spontaneously. On an average, 3 neutrons are released per fission. Well, let's now look at the fission of U-235 one more time. Uranium-235 is the chief fissionable isotope used in nuclear reactors and in certain kinds of bombs. In fact, the first bomb that was dropped in Hiroshima was a uranium bomb made of uranium-235. Now, watch this animation. A slow neutron is absorbed by uranium-235. What happens? It splits into 2 pieces. It releases, well, sometimes 2, sometimes 3 neutrons, and also a large amount of energy. Stray neutron is absorbed by uranium-235. Now, what remains is an unstable one, which splits into krypton and barium and krypton, and releasing a large amount of energy. So U-235 absorbs a stray neutron to become uranium-236, which is very unstable, and uranium-236 splits into nuclei of barium and krypton, releasing 3 free neutrons and energy. So I can write it like this: uranium-235 plus 1 neutron absorbs a neutron. It becomes krypton-92 plus barium-142 plus 3 neutrons and a large amount of energy. Now, we are not interested in all these things. We are only interested in the energy. Fission of a uranium-235 nucleus releases a large amount of energy. Approximately 200 million electron volt. I have converted that into joules there. Actually, that is not a lot of energy. 200 million electron volt, that is 200 times 1.609 times 10 to the negative 13 joules, which is 3.22 times 10 to the negative 11 joules of energy is released for each fission. Each time one nucleus undergoes fission, this is the amount of energy that is released. Now tell me, 1 gram of uranium-235, how many atoms are there in 1 gram? There are billions of atoms. Now, if all those billions of atoms undergo fission within a fraction of a second, what will be the energy that is produced? 1 gram of uranium-235, when undergoes fission, can produce enough energy to destroy the whole of the city of Pandagoda. Well, How much energy is released when 1 gram of uranium-235 undergoes fission? If 1 gram of uranium-235 contains 2.56 times 10 to the 21 atoms. There are trillions of atoms there. So what do? Each of these atoms undergoing fission will generate this much of energy. And therefore, the total energy released will be this energy per fission multiplied by the total number of atoms. Right? And that will be a staggering amount. Is 8.24 times 10 to the power of 10. In other words, it is approximately 82 billion joules of energy. And that is a tremendous amount of energy. And where did this much energy come from? From 1 gram of uranium-235. So 1 gram of uranium-235 can generate this much of energy. So if I have 5 kilograms of uranium-235, how much energy will it generate? It will generate enough energy to, well, to sink the whole of Southwest Florida. In fact, the bomb that was released in Hiroshima was about 6 kilograms of this material. And you can see the damage done with that bomb. So this is a tremendous amount of energy. Now, this is a tremendous amount of energy, and this much of energy will be enough to boil 250,000 kilograms of water. You can imagine the extent of that amount of radiation. Alright, let's now talk about chain reaction. What is the meaning of chain reaction? You see, when one uranium-235 nucleus undergoes fission, each time a uranium nucleus undergoes fission by capturing a neutron, free neutrons are released. And each of these neutrons will go and create fission in other nuclei. Look at that. The fission produced in one nucleus. Suppose of the 3 neutrons that are produced, if 2 of them go and produce further fission, so that means that will produce fission in 2 more nuclei. Now, the free neutrons produced in each will produce fission in 4 different nuclei. And the free neutrons produced in fission of those will go and produce fission in 8 nuclei. Look at the way the chain gets spread very fast. This way, a lump of uranium can undergo fission within a fraction of a second by setting up chain reaction. So if a mass of uranium-235, if one nucleus undergoes fission, the neutrons that are released in this fission can cause fission in 3 different nucleus. Now this diagram only shows 2, but normally there are 3 free neutrons. It can produce 3 fissions in the second round, and then there will be 6 fission in the 3rd round, then 18 in the 4th round. It will keep exploding like that in a chain. Now, this generation of neutrons can produce 27 different fissions and so on. Now, look at this, a chain reaction. Look, the neutrons going and creating more fission. Well, look, it doesn't take a very long time to produce fission in the entire material. Watch it again. 1 neutron produces the first fission. 2 fissions, 4, 16, 64. You can see the chain reaction has now taken over. I want you to watch that one more time. It starts with 1 fission, now 2, now 4, now 16. It happens within a very short time, and the entire material will undergo fission. Each of these neutrons can produce further fission, and a chain reaction sets in until the entire mass undergoes fission. Such a chain reaction is called a controlled chain. It's called an uncontrolled chain reaction. This kind of chain reaction is an uncontrolled chain reaction and normally used in producing a bomb. You see, if you want to make use of nuclear energy, then we need to control this chain reaction so that it will not become a bomb. All right? An uncontrolled chain reaction is used in the construction of an atom bomb. Look at the next concept called critical mass. What is the meaning of critical mass? You see, in order that the chain reaction may spread without control, the neutrons produced in each fission needs to be absorbed before they have a chance to escape. That means the fissionable material we use must have a minimum size. If the size of the material is too small, then before the neutrons have a chance to be caught by other fissionable nuclei, they will simply escape. That means you need a minimum mass in order that these neutrons may be kept inside to be caught by other nuclei. Now, this minimum mass to sustain a chain reaction is called the critical mass. In order that a chain reaction may be sustained within a given fissionable material, at least one neutron per fission should be available to be captured by other fissionable nuclei to produce fission. You see, some of these neutrons are going to escape, but if all of them escape, then the fission is going to stop. In order that the chain reaction may go on, at least one neutron should be available per fission. Now, neutrons produced in fission are fast moving, and there is a good chance that they escape before being captured for further fission. Now, if the mass of the fissionable material is too small, the neutrons have a greater chance to escape. The minimum mass that is necessary to start and sustain a chain reaction is called the critical mass of the fissionable material. That means in order that a chain reaction may start and keep on going, the mass of the substance need to be greater than this critical mass. In fact, when you have a fissionable material of mass greater than the critical mass, it is a bomb, because there will be uncontrolled chain reaction and the whole thing will explode. Well, we will now talk about a fission bomb. What is a fission bomb? A fission bomb obviously is made of a fissionable material. Do you remember the names of some fissionable material we talked about? Uranium-235 is a fissionable material. Plutonium-239 is a fissionable material. That means any of these fissionable material can be used to make a fission bomb. Now, how do you make a bomb? If I have an amount of fissionable material which is greater than its critical mass, it is the bomb. I cannot carry it in my hand. The moment I have a fissionable material greater than its critical mass, it is going to be a bomb. Well, uncontrolled chain reaction in a lump of uranium-235 or plutonium-239, which is greater than the critical mass, is an atom bomb. So once you have an amount of fissionable material which has a mass greater than its critical mass, it is an atom bomb. So how do we construct an atom bomb? Is it easy to construct an atom bomb? Well, the most difficult part of constructing an atom bomb is producing the fissionable material. It is not easy to produce uranium-235. As I told you, only a very small part of the naturally available uranium is uranium-235. And to separate that uranium-235 from the natural uranium is a very laborious, technology-oriented, expensive, and of course you need a lot of understanding of the process. That means it is not an easy process. And that is the reason why America is now saying Iran should not have the know-how of making a bomb. Well, I think Iranians already know how to make a bomb because it came from Pakistan. Pakistanis have already taught Iranis and North Koreans to make the bomb. Well, it gets a lot of expertise to produce the fissionable material. Well, once you produce the fissionable material, it's a question of assembling and delivering the bomb. Now, how do we do that? Now, here I have the diagram of a bomb. Actually, this was the bomb that was dropped in Hiroshima. It looks like this. You have to carry the bomb so that the fissionable pieces, there are two pieces of fissionable material. You see, this is a piece of uranium-235. This is another piece of uranium-235. And both pieces are below critical mass. That means as long as they are both below critical mass, they are safe. Because a chain reaction will not be sustained in there. Now, when you want to detonate the bomb, what you need to do is use a triggering mechanism that will fire this piece into the other piece so that the two pieces will fuse together, will become one piece, and then its mass will be above critical mass, and then the only thing you need to do is run away from it. Well, how did our pilots drop the bomb in Hiroshima? Well, what happens is you have a timed device. After dropping this, it falls through the air for some period of time. And after about 2 or 3 minutes, the triggering mechanism will fire this piece into that. And you have calculated where exactly and when exactly the triggering must take place. And by the time the bomb explodes, you can be away, sufficiently far away from there. So you can be safe. The device is safe as long as the two separate pieces are kept separate from each other. They are both below critical mass. And in order to make the bomb work, a detonator fires one piece into the other so that the total mass exceeds the critical mass. Now you have an atom bomb. So I have now taught you how to make the atom bomb. Is that right? So you can all go and make one? Well, you can, provided if you have sufficient fissionable material. Now, this is the fear now that in the international circles it has been a question for the past few years. After the breakup of the Soviet Union, there were a lot of fissionable material. You see, Soviet Union had big stockpiles of fissionable material. After Soviet Union broke down, it broke into small pieces. What happened to all the fissionable material? Now, is it possible that terrorist organization can get hold of those fissionable materials? Now, is it possible that somebody can carry these fissionable materials in a suitcase and carry it across to other countries? Well, these are all possibilities. Will it happen? Well, I think it's very unlikely. Even in a place like Russia, there are great safeguards for these nuclear materials. And there has to be safety precautions, and also very important to keep it away from people who can actually snoop into. So all these are secrets of a country that needs to be well taken care of. Now, what is a nuclear reactor? When you want to use nuclear energy for peaceful purposes, that is what every country says. Say, we are going to use our nuclear energy for peaceful purposes. Now, what are some of the uses, peaceful purpose uses of nuclear energy? But the most important peaceful use of nuclear energy is the production of electricity. The tremendous amount of energy that is released in fission, if we can control the fission and not to give up on a great uncontrolled chain reaction. If you can control the chain reaction, we can actually, you can make the chain reaction happen in a reactor, and the energy of these nuclear fissions can then be used to boil tremendous amount of water to produce steam, and that steam can be used to turn turbines to produce electricity. That is what is done in nuclear power stations. Now, to maintain a sustained controlled chain reaction, for every 2 or 3 neutrons released, only one should be allowed to produce further fission. You see, if there are 2 or 3 neutrons produced per fission, only one should be allowed to continue with fission. That means every time one fission occurs, that will give way to the next fission, that will give way to the next fission. In other words, the chain reaction will not happen. Now, therefore, what we need to do is, if the first nucleus undergoes fission, and if there are 2 neutrons produced, then only one should be allowed to produce further fission. Somehow we must remove the other one. In other words, we must use efficient neutron absorbing materials. And there are some good neutron absorbing materials. Boron is a good example of neutron absorbing materials. So a nuclear reactor uses good neutron absorbers like boron, so that extra neutrons can be absorbed. Only 1 neutron per fission is allowed to go and produce further fission. When fission is produced here, only 1 neutron is allowed to produce further fission, the other is absorbed. Now, this is how we obtain what is called a controlled chain reaction. So what happens in a nuclear reactor is controlled chain reaction. Now, if this ratio is less than 1, now this ratio is 1. What does that mean? Ratio is 1. For every nucleus that undergoes fission, another nucleus will undergo fission, 1 to 1. If this ratio is less than 1, it will die out. The chain reaction will not continue. So if the ratio is less than 1, the reaction will die out. But if the ratio is more than 1, it will go uncontrolled. So you got to be very careful. You cannot allow the reaction to die down. You cannot allow the reaction to go uncontrolled. So you have a critical path to keep where that ratio is 1. Now, nuclear reactions can be controlled by neutron absorbing materials such as boron that are used in nuclear reactors. Well, A nuclear reactor is a device in which chain reactions are initiated, controlled, and sustained at a steady rate. Now, all these processes need to occur in a nuclear reactor. You got to start a nuclear reaction, you need to control it, and you need to control that ratio so that it proceeds in a sustained manner. Do not die down, do not go uncontrolled, so that the reaction takes place at a steady rate. So there must be a lot of controls used in a nuclear reactor. So this is the schematic diagram for that. A slow neutron produces fission in 1 uranium-235, and these are the fission products: barium, krypton, and a lot of energy, and 3 neutrons. Look at that. And now you have the material used for neutron absorption is called the moderator. Now, what does the moderator do? The moderator, well, the neutron absorber will remove some, and the other neutrons are actually slowed down by the moderator, so that slow neutrons can then be absorbed by other uranium-235 nuclei. So there are 2 processes that need to happen in a reactor. One is excess neutrons need to be removed, and that is done by using neutron absorbers like boron. Then the neutrons that is made available need to be sufficiently slowed down so that other U-235 nuclei can capture it. And the material used for slowing down neutrons is called a moderator. So nuclear reactors are used for many purposes, but the most significant current uses are for the generation of electricity, and in rare cases for the production of plutonium. You see, there are many reactors. By using one fuel, we can generate another kind of fuel. You can produce plutonium. Plutonium is a fissionable material. You see, once you can produce enough plutonium, you can actually make a bomb. And that's the reason why when a country like Iran builds a nuclear reactor, we got to make sure that they do not go and do this, produce plutonium from the spent fuels. You see, once a country starts reprocessing the spent fuel, the reprocessing process is for the purpose of producing plutonium. Now, once they start producing plutonium, it is clear that they are aiming to make a bomb. Is that right? And that's what we need to be careful. Now, there's nothing wrong in a country building a nuclear reactor, because every country has the right to use nuclear energy to produce electricity. But if a country starts producing plutonium, then the atomic weapons are going to be proliferated, and the proliferation of atomic weapons is going to spell out the end of our civilization. So it is very important that less and less countries have the know-how to produce these kind of materials. Now here I have the schematic diagram of a nuclear reactor. I want you to look at the various parts of it. Now, this is the normal dome that you see. When you see the picture of a nuclear reactor, you see a big dome. That's a big concrete dome. You see, there are many deadly radiations that originate at the core of the reactor. We don't want those deadly radiations escaping to the surroundings. So you have big steel chambers surrounded by thick concrete walls. So we got a good shielding in there. And this is the inner chamber where the nuclear fuels are. You see these black material there is actually uranium rods. They are fuel rods, and these are control rods. Control rods are neutron absorbing materials. When all the control rods are pushed in, no reaction will happen. When you want to start the reactor, you start pulling out the control rods so that free neutrons are available to start the chain reaction. Now, when the reaction starts, what happens is the energy produced in each fission. Now, remember what I told you. 1 gram of uranium undergoing fission can boil billions of kilograms of water. So, when nuclear fission takes place here, the amount of heat produced is absorbed by this water that is circulating through this chamber. And that water will boil the water in an outer chamber. Look at this water, the blue. That water boils, producing the steam. And this steam will turn the turbines, because the turbines turning will produce electricity, which is then distributed. So the energy of fission is collected by circulating water. It's called the primary water loop, which then exchanges that heat to the secondary water loop. This is the secondary water loop, and that water will boil. When boiling water will produce steam at great pressure, and that steam at great pressure is used to turn turbine, which then produces electricity. Now, this is the containment building, which contains all the technologies of the nuclear reactor. Now, if you are not careful, if the temperature is not regulated, if the heat is not removed properly, a nuclear reactor can melt down. Now, what is the meaning of melting down? If a nuclear reactor melts down, it is like a bomb. So, the whole structure will collapse and it will be like a bomb. This is what happened in Chernobyl in 1993? That's right. In Chernobyl, there was a meltdown of the nuclear reactor, and hundreds of square kilometers surrounding that area is still uninhabitable. And there are still people suffering from cancer and lost limbs, and many hundreds of thousands of people died. So a nuclear reactor has safety concerns. And that's the reason why America has not built a nuclear reactor in the past 35 years. Because whenever the government tries to build one, there are always local protests. We don't want a nuclear reactor in our neighborhood. Now, how many of you want a nuclear reactor in your neighborhood? Well, I don't mind having one because I know it can be built with proper safety. And if it is run with proper safety, it is a means of producing electricity for many, many years. And in France, 80% of the energy used in France is produced from nuclear energy. So it is possible. Okay, heat is produced in a nuclear reactor when neutrons strike uranium atoms, causing them to fission in a continuous, controlled chain reaction. And neutron absorbers are called control rods, are used among the fuel assembly to control the rate of reaction. When the control rods are pulled out, the more neutrons are available and the chain reaction speeds up, producing more heat. If you want to slow down, you pull the control rods in. When they are inserted into the core, more neutrons are absorbed and the chain reaction slows or stops, reducing the heat. Now, most commercial nuclear reactors use ordinary water to remove heat. You see, this is ordinary water used to remove heat, which is then used to boil water in a secondary chamber. All right. In a PWR, pressure water reactor, now the heat is removed from the reactor by water flowing in a closed pressurized container. That's why it's called the pressurized water reactor. Now the heat is transferred to a secondary loop through heat exchanger. Water boils in the heat exchanger, producing steam at high pressure, which then turns the turbine to produce electricity. And that steam is condensed back and used again. The water is reused over and over again. Now, there is another kind of reactor called BWR, boiling water reactor. Now here, water is directly boiled by the chain reaction. You can see the water which is inside the reactor, the fuel rods are inside that water. And this water boils, producing the steam and turning the turbine. What is a breeder reactor? A breeder reactor is a reactor which breeds more fuel than what they consume. Well, that's a very interesting concept, is that right? Under appropriate operating conditions, the neutrons given off by fission reaction can actually breed more fuel from otherwise non-fissionable isotopes. You know that uranium, the fuel rods that are used are not pure uranium-235. They are called enriched uranium. So the fuel rod contains uranium-235 and uranium-238. Uranium-235 is readily fissionable. Uranium-238 is not readily fissionable. Now, the neutrons that are released in fission, if absorbed by this non-fissionable isotope of uranium, they can be made into plutonium. Now, the most common breeding reaction is that of plutonium-239 from non-fissionable uranium-238. When the uranium-238 absorbs a neutron, it becomes radioactive, and as a result of radioactivity, plutonium-239 is produced. Now, this is the process. A uranium-238 absorbs a neutron and becomes beta-active. Now, you recognize what that is. When an element emits a beta radiation, its atomic number increases by 1. So, uranium-238, uranium, the atomic number is 92. As a result of a beta radiation, uranium now becomes an element of atomic number 93. Now, and then that will emit another beta, which will then give plutonium of atomic number 94. And that is a readily fissionable material. You see? So, using a non-fissionable material inside the reactor, we can now produce a fissionable material. So, what is this reactor doing? This reactor is breeding fissionable material. You see? From a non-fissionable material, uranium-238, it is breeding plutonium-239 that is fissionable. Such a reactor is called a breeder reactor. The reactor core consists of thousands of stainless steel tubes containing a mixture of uranium and plutonium. about 25 to 20% fissionable plutonium-239. Surrounding the core is a region called the breeder blanket, consisting of tubes filled only with uranium oxide. You know that before we went to war with Iraq, the government accused Iraq of purchasing large quantities of steel tubes. Now, the assumption was that those steel tubes are going to be used to construct these breeder reactors, because the type of steel tubes they purchased were those kind of very fine quality. But apparently now there is no proof that they bought those for breeder reactors. Such a reactor can produce about 20% more fuel than it consumes by breeding reaction. That means this reactor, as it keeps on consuming fissionable material, it keeps producing more fissionable material. It produces more fissionable material than it consumes. And such a reactor is a breeder reactor. And once the fuel rods has been active for some years, you can remove them and reprocess them to remove the plutonium. And plutonium is a much more effective fissionable material to produce a bomb than uranium-235. So uranium-238, after capturing a neutron, emits two beta particles, one after the other, transforming into plutonium-239. This is the process that happens inside the breeder reactor. So plutonium-239 is a very highly fissionable material. Uranium-238 absorbs a neutron, becomes uranium-239. It gives off a beta particle, becomes neptunium. That gives off a beta particle. Remaining is plutonium. So this is what happens. Uranium-238 absorbs a neutron to become uranium-239. It gives off a beta to become neptunium of atomic number 93. And neptunium will give off a beta particle. It becomes plutonium-239. Alright? This plutonium-239 is a much more spontaneous fissionable than uranium-235 is, and therefore much more effective in making bombs. Now, one of the bombs that were dropped in Japan during the Second World War was a plutonium bomb. The first one was a fission bomb, and the second one was a plutonium bomb. Plutonium-239 is separated from the spent fuel in a reprocessing plant. Now, this is again, that is, if any country is building a reprocessing plant, they're called centrifuges. You know that Iran has now said they have 2,000 odd centrifuges. Centrifuges are actually used to separate plutonium-239 from the spent fuels. Of course, if they are using centrifuges, they are actually producing plutonium, and therefore they are producing materials that can be used to produce a bomb. Well, so far we talked about fission, that is, large nuclei splits into two pieces in trying to achieve stability. In the same way, lighter elements can fuse together to become a bigger nucleus. Then again, large amounts of energy are produced. That is nuclear fusion. Nuclear fusion is the energy producing process which takes place continuously in the sun and the stars. What is the mechanism of energy producing at the core of a star? The temperature at the core of a star is about 15 million degrees Celsius. And in order that fusion may happen, hydrogen colliding with another hydrogen can fuse to become helium. Helium colliding with another helium can fuse to become carbon. You see, smaller elements fusing to get bigger elements, and the process of fusion generates large amount of energy. All the energy in the universe that is released by these stars are released due to nuclear fusion. In the core of the sun, at the temperature of about 10 to 15 million degrees Celsius, hydrogen is converted to helium through providing enough energy to sustain life on Earth. In fact, all the energy that we receive from the sun is from this process, nuclear fusion. What is happening in the sun is fusing hydrogen together to form helium. And that's how all the energy that we get is being produced. Now here we have a deuterium. A deuterium is a hydrogen isotope. A deuterium and a tritium come together to form an isotope of helium. And there is a tremendous amount of energy produced. The most suitable reaction occurs between the nuclei of the two heavy forms of hydrogen, that is deuterium and tritium. When a deuterium and a tritium are fused together, you produce an isotope of helium plus a tremendous amount of energy. At the temperatures required for the deuterium-tritium fusion reaction, and that temperature is about 15 million degrees Celsius, the fuel has changed state into plasma. You see, the reason why we are unable to generate energy from nuclear fusion is that fusion will not occur under ordinary temperatures. A nuclear fusion can be created only at tremendously high temperatures like 15 million degrees Celsius. How will we produce such a tremendous temperature on the surface of the Earth? If we can, then fusion energy is the cleanest energy. You see, fission energy is not clean because nuclear fission produces the fission products which are very highly radioactive. And storing away and putting away these fission products is a great problem. And that is one of the reasons why we haven't been producing nuclear energy for quite some time. The safety concerns as well as the concerns about storing away the fission products. But if you can get nuclear fusion going, that is the best way to produce energy for our needs. But we are not there yet. We haven't generated the technology know-how so that we can produce fusion at a lower temperature that is attainable on the surface of the Earth. Okay, since most practical nuclear fusion reaction for power generation seems to be deuterium-tritium reaction, the source of these fuels are important. Where do we get these fuels? Actually, there is abundance of this available. Seawater contains an abundance of deuterium. The tritium part of the fuel is more problematic. There is no sizable natural source since tritium is radioactive with a half-life of about 10 years. So tritium will degenerate into other forms. Now, it would have to be obtained by breeding the tritium from lithium. Now, given that it is possible, but still obtaining the fusion, to get the fusion going, the high temperatures needed for that is difficult. In a plasma, plasma is the state of matter which happens at a very high temperature. At the order of 15 million degrees Celsius, these atoms do not exist as normal atoms. They are stripped apart, and that is what we call the state of plasma. Some advantages of fusion reactions are: fusion is a vast new source of energy. Well, if we can tap that source of energy, all our energy problems will be solved. Let's hope that in the near future we will be able to do just that. Is that right? Conquer that technology. No atmospheric pollution leading to acid rain or greenhouse effect. That's what I told you. The fusion energy is a clean source of energy. There are no pollutions created. There are no spent fuels to be discarded. There are no safety concerns. All those are not there anymore. Waste disposal problems are minimized. Less radioactive contamination. So all these problems are actually solved if we can get the nuclear fusion going. Well, that seems to be very far away. So at the moment we have gone through briefly the concept of how nuclear energy can be produced and used for peaceful purposes and also for military purposes. Alright, now this is the end of Unit 4, and this is the time. Go back and do all the homework one more time. Look at the practice test and get ready for Unit 4 test. Alright, now we have one more unit left, Unit 5. I will get back to you with that in a short time.